Okay, guys, so here's lesson 3 out of energy and momentum. So we're going to start taking a look at the work-energy theorem. Now, we've already said one thing. We said that work was defined as can be defined as a change in energy. So if you put work in, the energy of a system is going to increase. If you do negative work, or like, for example, the case of friction is working against whatever you've got, it's going to take energy away from the object. In the case of friction, it'll take it away in the form of heat. So this gives us the basis for what we call the work-energy theorem. And so that actually looks a little bit different than the equation that we've got written. What that ends up looking like, so we're going to manipulate this here. Work is equal to a change in energy. Well, this is delta, meaning mathematically this means final minus an initial. So let's start to manipulate this thing. So we've got energy final minus energy initial. And the way that the work-energy theorem actually ends up looking is you take this initial energy expression and you add it to the other side. So we're going to get energy initial plus whatever work is done is going to equal your final energy. Excuse me. And this is what we call the work-energy theorem. This shows up on your guys' formula sheets. So if I look here, I'm just going to isolate some stuff. So this section was kinematics. This section was dynamics. And here we are now in, we're going to go like this. This section is where we are now in work and energy. So you can see this, the expression that we're going to go for is this guy. Well, it's these two here. It's this energy initial plus WNC. I'll explain what that NC means here in a bit. And it's going to actually end up giving us, we're going to use this part of the expression as well. So this is where we're at on your formula sheet. So we say that a system has energy if it can be, if it can do some useful work. There are many forms of energy, but we're going to deal with 4 of them specifically: kinetic energy, potential energy, heat energy, and chemical energy. Now, kinetic energy is the energy in a moving object, hence that word kinetic. Potential energy is the idea that if we let this thing go, it will start to move. It has the potential to do energy, and so there's a couple different kinds of potential energy. This could be gravitational potential, or it could be spring potential. We are not going to look at spring potential. We're just going to look at gravity. There's heat energy, so the energy of a hot object. Basically, we're going to isolate this to friction. And then we've got the chemical energy. So kinetic energy, you had an expression for, you should have looked at it in grade 11. Kinetic energy is half mv squared is the expression that we use for that. The potential energy, the height energy for an object, is given to us by mgh. And we've already said that heat energy is friction. So I'm going to work through a proof for you guys here of why this is true. So sometimes when we do work, we make things move, and so we're gonna prove this to you that this is a change in energy. So we're going to start here with our definition for work. So work is equal to a force times a distance, but we also know that F equals ma. So we're going to take this mass times acceleration, we're going to replace F in this expression. So we're going to get work equals mass times acceleration times our displacement. Now there's a trick here that my physics profs at university always hated it when we called it a trick. It's a technique, they would say. So the technique here is we're going to make this look like we want it to look, we're going to multiply by 1. And the 1 that we're going to multiply by, this will make sense here in a second, is this times 2 times a half. Now, this 2 times a half is 1. So when you multiply by 1, it doesn't actually change the expression that you have. So when we multiply this by 2 and multiply it by a half, it doesn't actually change what we've got here. And so what we can do is we can start to move things around. We can look here and we can say, okay, well this, make sure I include the right pieces here. It's this 2AD piece that we want to look at here. So I'm going to pull this over here. So 2AD, we actually see that show up somewhere. We've seen this in the kinematic equation, VF squared equals VI squared plus 2AD. So we're going to take this 2AD, we're going to isolate for it over here, and we're going to get a VF squared minus VI squared equals 2AD. And then we're going to take this expression here, and we're going to put it back in there. And so what we're going to get here is that our work, I'm just going to scribble this out here and maneuver this. Well, basically, I'm going to write down exactly what was there. Our work is equal to m times VF squared minus VI squared times a half. That's all that's left. These two on the outside. This guy here in the middle is replaced with this. And then I'm going to move this around here a little bit. We're going to get work equals, because you can multiply in whatever order, 1/2 mv final squared minus 1/2 mv initial squared, which means that work is equal to your kinetic energy at the end minus your kinetic energy at the beginning. And oh look, that's exactly what we started with here. Work equals a change in energy. So this is where that idea comes from. So the kinetic energy of a moving object we've already seen is 1/2 mv squared, something you should have looked at last year or whenever you did grade 11. I'm not going to do this proof here. I mean, if you want to see it, I can do it for you later. Just fire me an email or make a comment on this video. And this guy here, potential energy, we've already seen this. This is just MGH. So let's actually do some stuff with this. I got a couple examples for you guys today, and then you can work on some of the questions I've assigned. So here we go. In general, when we do work, we can give an object both motion energy and height energy. So this shows up like, so work is equal to whatever potential energy and whatever kinetic energy that you've given. But however, if the object already had some height or some motion, the work merely changes the amount of energy that's present. So this will make sense here in a second. So we already have the work energy theorem that said that my initial energy plus my work equals my final energy, and this can show up a bunch of different ways. We've already said that energy can be potential, energy can be kinetic, energy can be heat energy. Generally, how this is going to look this year, or in Physics 12, is that your initial energy is going to take up, it's going to be whatever your kinetic energy was to start, whatever your potential energy was to start. Your final energy is going to be whatever your kinetic energy is at the end, whatever your potential energy is at the end. And generally, when we talk about heat energy, that gets addressed, or that gets absorbed into this term here, because we look at friction as pulling energy out of the system or doing negative work. So we're going to deal with friction and heat right there. So we're going to look at a couple examples of some problems and see how this thing goes. So to solve problems with the work energy theorem, we want to visualize what's happening. So we always want to draw a picture. We want to decide what forms of energy are present at the beginning and at the end, and we want to apply the work energy theorem to those ideas. One of the things that we do here now is when we're dealing with potential energy is pretty vague, and if we were all in class, I'd have some hand-wavy kind of demonstrations to show you what I mean here. But at this point, you're just going to have to kind of take my word for it. So potential energy depends on what you view to be zero. So for example, if I had an object sitting on a flat surface, you might say that that thing has no potential energy. It also has no kinetic energy because it's just sitting on some surface. But what if this surface had an edge and I just moved this guy a little bit so he was over here? And now all of a sudden, this guy has a potential to fall. He didn't change position very much. Like maybe this was a table and we had the ground right here. All I did was I slid this guy to the right a little bit, and now I'm holding him here. And now all of a sudden, we would say he's got potential energy. But nothing has really changed here, other than the fact that now this guy could fall, whereas he couldn't fall here. The height of the object above this pink line hasn't changed. What that allows us to start to do is recognize, hopefully, that this idea of potential energy is pretty abstract. And what that allows us to do is it allows us to define what we want to call a level of zero potential energy. And that's going to change for every question that we look at here. So for this guy, for this particular example, a person doing work throwing a ball, when we were talking about kinematics, this is the section that we wouldn't ever really care about. All we cared about is now the ball leaves the hand with a particular amount of velocity. We would call that VI. Now in this section is where we're going to start to talk about the beginning part. You're about to throw the ball. Now you do throw the ball. What's going to happen here? When we look at problems like this, because if you look here, at least in this part of the problem, the ball's height hasn't changed above the ground. What we can do is we can say, to make the mathematics easier, we could say, well, let's call this level here potential energy equals 0. We can ignore it entirely. And I'll show you why that's true. I'll do it two different ways. If we call that potential energy equals 0, well, then our expression is going to look like this. I want to know I've got some energy at the beginning of the problem plus work being done to make the ball move forward is equal to my final energy here. And what is that? Well, at the beginning, this thing's at rest, and if I'm calling this potential energy 0, then this thing has no energy. We're going to do some work to it, and it's going to start to move forward. And again, because it's at the same level, we can say, well, there is no potential energy at this level. And so it's just going to have kinetic energy final, and so we can say that my work is equal to half mv squared. And if we knew the mass of this object, we could figure out how fast it's moving based on how much work we put into it. That's one way we can look at this question. Another way we can look at this question, just to kind of prove to you that the idea of potential energy is arbitrary here, is we could say that this potential energy is equal to 0, and that this here represents the height above the ground. And so if we look at it here, this object at the end of the problem is still the same height above the ground. So I'm going to do the same question here, but in red. So now we're going to use the work energy theorem, energy initial plus some work being done is equal to my final energy. Now, initially, this thing has no kinetic energy because it's at rest. But now if we look at the red lines, we can say, okay, well, this does have some height above what we're calling potential energy 0. So now we can say at this point, it does have some potential energy. So we're going to have potential energy initial plus work equals, and now at the end here, it does have some height above potential energy 0, so we're going to have potential energy final plus, it now is moving, so it's got some kinetic energy at the end as well. But let's fill in what we've got here. Potential energy initial is mgh initial plus whatever work we did is equal to mgh final plus half m, that's a half of the 2, mv final squared. But if we look here, my height initial and my height final are exactly the same. So I can subtract this guy over here, and that means this guy and this guy are going to cancel, and so I'm going to get my work equals 1/2 mv final squared, which is exactly the same expression I had here before. At least it is now. Okay, so you got to be careful how you're using this idea of potential energy, but what I want you to recognize is as long as you're consistent, it doesn't really matter where you put it because you're gonna handle it kind of regardless. So let's get a couple more of these. If I have brakes that are doing work slowing down a car, this thing has some initial velocity, it has some final velocity. But there, you can see here that the height of the object isn't changing. And so if I call this h equals 0, or potential energy equal to 0 at that point, then this thing is just going to look like, if I've got my energy initial plus my work being done equals energy final, then this thing only has kinetic energy at the beginning plus work being done is going to equal my kinetic energy final. And if this thing is slowing down, then my expression for work is going to be negative because it's taking energy out of the system. For this guy here, a cyclist doing work moving up a hill, we can see he's initially at rest here. So the expression here is going to end up looking like a few things. Well, first we have to decide where we want potential energy equal to 0. Well, in this case, this would make the most sense. Height here equals 0. Height here equals, well, some value. We'll call it h final. So if at the beginning the height is 0 and this thing's at rest, then my potential energy at this point is equal to 0, and my kinetic energy at this point equals 0. So we can say that there is no energy. It's kind of arbitrary, but there is no energy at the beginning of the problem. So if I'm going to use my work energy theorem, energy initial plus work equals energy final, and then to start to manipulate this equation, there is no energy at the beginning. So we're going to get work equals, and we can see that this guy's moving and he has increased in height. So there's going to be potential energy present and kinetic energy present here at the end. So we're going to get mgh final plus 1/2 mv final squared. This is how this is going to look. A couple more examples of the same ideas. An elevator lifting passengers, we can see that it's at rest to start and it's at rest at the end. So all that we're going to get here, and if we say that, well, my height is equal to 0 at this point, and it's being raised to some height final, because they're both at rest at the beginning and the end, my kinetic energy initial equals 0, my kinetic energy final equals 0. So all this thing is doing is changing its potential energy. So I'm going to have my energy initial plus my work equals energy final. I've got, at this point, potential energy equals 0 as well, so there is no initial energy. Work was done to increase the potential energy, and trust me, if that cable breaks, this person's going to realize all sorts of ways that he has potential energy. Another one, the parachute here opening versus the parachute fully open. We can look at a few things here. So it depends on what we want to call 0. Now, we don't know how high above the ground this person is, so it's not like we could call the ground 0. So what we're actually going to end up doing is we're going to say that this level here at the end of the problem is what I want to call h equals 0, which means this here, we're going to call this height h. And if we actually think about what's happening here, so this distance here is just h. It's starting here and ending here. So this becomes our h final is equal to 0, which means our initial h is going to be, or initial height above what we're calling 0 is, I'm just going to call it h. So that means at this point, as the parachute's opening, this guy's obviously moving. So we're going to have kinetic energy here. We're going to have potential energy here because there is some height above what we're calling 0. Now down here, we're just going to have kinetic energy. And because this is the level that we're calling 0, we're going to say there is no potential energy at this point. Pe equals 0. So then the work energy theorem is going to look like this. Energy initial plus work equals energy final. So my energy initial is going to be my kinetic energy to start plus my potential energy at the beginning plus whatever work is done to slow this person, in this case, so that's going to be negative work, is going to equal my potential energy at this level we've said is 0. So that's going to equal my kinetic energy at the end. So let's do, I think I've got 2 examples for you guys. 3 examples for you guys. And then we can move on from here. Or then you guys can work on this stuff. So a 5-kilogram cannonball is launched by a cannon. Sometime later, the cannonball is 8 meters off the ground and moving at 10 meters per second. We want to find the work done on the ball during launch. So here's what we've got set up here. We've got the pictures already drawn for us. We just need to define a few things here. So let's define the ground, this guy here, as being my height equals 0. Often the ground at height 0 is the thing to do, because if we recognize what's going on here, we're told that this is a height of 8 meters, so it's really easy to say, well, this is 0, which is going to give this object at this point some potential energy. And we can take a look at what's going on here. This is the initial state of the problem. He's just kind of sitting in the tube waiting for things to happen. This is the final state of the problem. Eventually the ball is here. So the question is, what else is going on here? The idea is that there's work being done at this point. So we have our initial state plus our work is going to give us our final state here. And so we've got my energy initial plus work being done is equal to my final energy. At this point, this object is at rest, and it has no potential energy because it's sitting at what we've called h equals 0. So there is no initial energy. Work was obviously done. There was a chemical explosion here that launched this ball forward. And so we know that the object at this point is moving, and we know that it's above the ground. So here at this point, there's going to be kinetic energy, and there's going to be potential energy. So at this point, we've got work equals 1/2 mv final squared plus mgh final. I should actually put F subscripts on those guys as well. And so now we can see how much work was done. We know that this is a 5 kilogram cannonball. At this point, it's moving at 10 meters per second, and it's 8 meters above the ground. So that's going to allow us to solve this. So I've got 1/2. My mass was 5. My velocity at the end here was 10 squared plus my mass here is 5. G is 9.8. And my height above the ground is 8 meters, which means at this point, this is just, you shove that into your calculator, and you're going to see here that the work done to get the ball to this state was 642 joules. Let's look at a couple more. At this point, we went straight to B. Find the work done on the ball during the launch, and this is everything that this is the procedure, the way you think these things through. So let's flip the page. Let's do another one. This example here, the point of this, so there's an example 5 here. The part A says to find the work done by a motor using work equals force times distance. And this guy down here says to find the work done by the motor using the work energy equation. And so the purpose of this example is to show you the equivalence between two statements. We want to show that work equals force times distance is equivalent to, that's that symbol, work equals a change in energy. And so there's 2 ways that we can actually do these problems. I don't particularly care unless I specify which technique I want you to use. Generally, I don't care which technique you choose to use. So let's take a look at how this works. We have a motor pulling a 250 kilogram mass up a frictionless 8-degree, 20-meter long ramp. And the mass moves up at a constant 1.75 meters per second. And so let's take a look at what that means, or what that gives us, rather. So if we're going to use work equals force times distance, we need to figure out what the forces are, which means we have to do a free body diagram on this thing. So again, this object's on an incline. Be careful how you set this up. There was all sorts of mistakes last chapter with how this worked. So we're going to have Fg acting straight down. My normal force is perpendicular to the ramp. So this guy's going to act off on some angle. And we've got an applied force, call that F. It's the force from the motor, well, let's call it FA, F applied. That's my free body diagram. Now you got to be really careful how you draw the component triangle for Fg. This guy is we have 1. I'll call this Fg perpendicular because it's perpendicular to the incline, which means it's opposite my Fn. We're going to call this Fg parallel, because it's parallel to the incline, and this is my 90-degree angle in here, which means this guy right here is 8 degrees. I'll zoom that in so you can see it a little better. I hope that you can see, make that a little bit clearer. So we're told that this thing is 250 kilograms. So that's going to give us a value for, I'll just go back to orange, a value for Fg of 250 times 9.8. I'm just going to leave it that way. My Fg parallel is going to be 250 times 9.8 sine 8. This guy here is going to be, the perpendicular one is going to be 250 times 9.8 cos 8. My Fn is equal to and opposite my perpendicular component, so that this Fn here is also going to be 250 times 9.8 sine 8. And there's some important things to recognize here. We are told that the mass moves up at a constant 1.75 meters per second. Constant velocity, which means my acceleration here equals 0. If my acceleration here equals 0, that means my Fa is going to be equal to and opposite the only other force acting in this plane, which means my Fa is going to be equal to and opposite this Fg parallel down here. So this guy is going to be equal to Fg parallel. So, and the other piece of information that we know is that this ramp is 20 meters long from the beginning to the end. And so now we've got a force acting on our ramp. We know the length of the ramp, so we can figure out the work done to pull it along the ramp. So I'm going to have my work equals my force times distance. In this case, my work is equal to the applied force times the distance, which means I'm going to have my applied force is equal to Fg parallel, so that's this guy here. I'm going to have 250 times 9.8 sine 8 times the distance is 20 meters. So if you run that through, you're going to get the work done here is equal to 6,819.48 joules. So that's using work equals force times distance. We have to do a bunch of trig here to make that happen. Now we're going to do the exact same question, except instead of using work equals force times distance, we're going to talk about it being a change in energy. So I'm going to slide this down here, and then I'll zoom out after I've done this one and show you that, just kind of sum up that they're all equal. So I've got the same situation here. I've got a block. We know the mass of the block. I'll just condense this, is 250 kilograms. That doesn't change. We know that there's a velocity here of 1.75 meters per second. It's constant. So here the velocity is also 1.75 meters per second, but we do know that this thing's going up. Well, we don't know how much this has been. Well, we can figure this out relatively easily. This thing is being raised. So this thing here, we know the ramp. This is just a right angle triangle. So this guy here is 20 meters. So if we're going to use work and energy, the types of energy we have are kinetic and potential. So we need to figure out how high this thing has been raised. So this height is just going to be the hypotenuse times the sine of 8. And give me that height there. And I'm going to call this h equals 0. And so now we can go through and we can use potential energy and kinetic energy in our, well, basically we're using the work energy theorem. So I'm going to have my initial energy plus whatever work is done is equal to my final energy. At the beginning, it's here at the bottom, moving at 1.75 meters per second. So at this point, it has some kinetic energy. Work is being done. At the end here, it's still technically moving, and it has been raised some height. So there's going to be kinetic energy here at the end, plus potential energy. So we can go through and we can fill out what this expression is. Kinetic energy is 1/2 mv initial squared plus work is going to be 1/2 mv final squared plus mgh final. And now we're going to fill this in with the values that we were given in the problem. So we're going to get 1/2 times 250 times 1.75 squared plus whatever work is done. It's still moving, so 1/2 250 1.75 squared plus 250 times 9.8 times 20 sine 8. Now look at what we have here. These two expressions are exactly the same and they're on opposite sides of the equal sign, so they're going to cancel. We can subtract this one over, and we're going to see that this guy and this guy disappear, which is going to give us an expression for work. Move this down a little bit here. Our work is going to equal 250 times 9.8 times 20 sine 8. Well, let's see what we've got here. Let's just zoom that out a little bit, slide this down a little bit here. Where is it? It's going to show up there eventually. Let's zoom this out a little bit. Doing this question two different ways, we can see here, and I'll just put this value, put that W there. So my work in my previous question, and you'll see now why I left it this way, is 250 times 9.8 times sine 8 times 20. Down here, I've got 250 times 9.8 times sine 8 times 20. So these two expressions, two different ways, or we have the same expression two different ways. So what this implies is that my work equals force times distance is equivalent to work equals change in energy. And if you run this through, you're going to see here that the work is equal to 6,819.48 joules. So it doesn't matter which one you use as long as you approach the question using the techniques that you've been given here. If you flip the page, you'll see that there's a bunch of technical comments. I'm not going to go through. This. If you want to give it a read through, you're welcome to do that here. Down here is where we'll end up seeing this N-C thing. All of that. So all this I will address. So it says basically the argument it's given up here above this is that as things are changing in your system, as if it's dropping straight down or if it's dropping down an incline or a curved path, it ultimately doesn't matter which one of these paths it's taking. You're still starting with some potential energy, you're ending with zero potential energy. There's the energy of motion here. The trigonometry gets a little bit weird, and in this case, it gets really weird because we can't actually. You guys don't have the mathematical skills to address this part yet. What the argument here is making is that we can look at our energy initial as kinetic plus potential. We can look at our energy final as kinetic plus potential, and then use this work term to look at the change in energy by all other forces. The language here in physics is that these other forces are changing the energy of a system. And so we're going to look at, or actually you should have looked at in Physics 11, this idea of the conservation of energy, because energy is changing from the beginning to the end of our isolated system. We say that these forces are non-conservative. I mean, they're changing the energy that's present. We're not considering conservation of energy. So this N-C just means that there is work being done by non-conservative forces. Generally, I'm not going to be that picky. This is the same as saying my energy initial plus whatever work is done by some other force or object is equal to my energy final. I'm not going to be as picky as saying, well, these are non-conservative. That's implied, but I'm not going to go into that level of detail. These two expressions are exactly the same. So for this lesson, let me get you guys to, I'll give you the questions that I want you to take a look at out of here. The questions I'm going to assign to you are this. So for this lesson, I want you guys to look at 1, 2, 4, 6, 10, and 11 is the content for this particular lesson. If you get this done and want to do so, this lesson, If you find yourself with time and want to review some of the older concepts, you can also look at the following questions. Question 8, question 14, question 15. Question 8 is looking at power, so that's a review of either yesterday or the lesson 2 or I think it's lesson 2, maybe lesson 1. It doesn't matter. One of the previous 2 lessons that you've looked at. Question 14 is a pulley tension question, so it's a review of the dynamics section. Some of you would benefit from looking at that question. And then 15 is a projectile question, which is a review of the very first chapter that we looked at. So this would be a review of chapter 1, this is a review of chapter 2, and this is a review of lesson 1 and 2 from chapter 3. So there you go. Take a look at that. Email me whatever questions you've got, and I'll make some videos for you guys addressing any of your comments, questions, or concerns.